There we go. I think I just turned recording on. We'll see. Let's define a function called bootstrap. So this bootstrap is going to take an original sample. It's going to have label, and it's going to have replications as inputs. And let's see what the documentation tells us. Returns an array of bootstrapped sample medians. Original sample is a table containing the original sample. Label is the column label. So if you think of it as a data frame, it's the data frame column. Replications is how many times you want it to do it. And then some goofball here said modified by myself for missing dependencies from the original script. So there is a instance called just one column. Medians, we're going to make an array, and then we're going to start appending to the array. So for I in NumPy, a range of replications, which is an input value, we'll take the just one column sample and put it into something called bootstrap. And then in bootstrap, we'll take the 0th column, we'll find the 50th percentile of that, and we'll assign it to a value called readSample median. And then we're going to assign resample medians to the variable medians by appending it to itself, and then we return the value. So all this does is it does this thing as many times as we tell it, and it keeps track of our counting scheme. So let's load that in. Let me change this to a 5 to make sure it runs. Okay, so I'll return this to 5,000. So we're going to do 5,000 resamples, which is kind of a lot. And we're now going to build a histogram of those 5,000 resamples. And we'll also, since we know what the population median is, we're going to put it as a red dot on the histogram. So we generate that, and here's our 5,000 resamples. And now we have some idea of the variability. So the population median lies somewhere between 100,000 and 120,000. And we actually have the ability to somewhat quantify that. So it's important to remember this red dot here is fixed. It's the population median, and the empirical histogram is the result of random draws and will be situated randomly with respect to the red dot. So if I were to run the resampling again, replot it, histogram change appearance, but pretty much kind of the same stuff. So how often does the empirical histogram of the resampled median sit firmly over the red dot and not just brush it with its tails? So first you have to decide what's meant sit firmly. In other words, let's take it to mean the middle 95% of the resampled medians contains the red dot. So the two ends of the 95% can be determined by using our percentile function. We'll take the 2.5 percentile, the 97.5 percentile of the bootstrapped medians, and we'll just print them. So the 95 percentile interval estimate of the median of the original population is 103,700 to 115,100. So we have a 95% probability that the true value lies within that. And in this particular instance, the 110,000 indeed lies within that interval. So the interval and the population median can be displayed on the histogram. This one has some pretty cool plotting stuff. So the this yellow bar represents the interval estimate. And let's see what happens if I bump up the line width. And just so y'all don't think I actually know what I'm doing, I do a lot of cut and paste, and as you can see, modify. So I use the CCMR method that we invented in this class. Yeah, I still get the same warning. So this yellow bar represents our interval estimate. So in this particular instance, our interval estimate indeed captured the true value. So the next obvious question, well, was that just a fluke? Well, let's find out. Let's just run it all again. Hopefully I'll get lucky and waiting for my poor little computer to catch up. The histograms change shape again, but let's automate what I just did because we don't want to do that many times. To see how frequently the interval contains the parameter, we have to run the entire process over and over again. Specifically, we're going to do the following 100 times. We're going to draw an original sample size of 500 from the population. We'll carry out 5,000 replications of the bootstrap process and generate the middle 95 percentile. And what we'll end up with is 100 intervals. And then we're going to count how many of them contain the population median. So the way we picked it using the particular percentile, 2.5 to 97.5, we should get about 95% of the intervals will contain the median, but we're not guaranteed that. So here's the script to do it, and I'm not going to run it yet because I know it takes 4 minutes to run, but I'll read it to you. So we get the left ends and the right ends, and we're going to create arrays to store those values in. Total compensations we're going to take from the SF 2015 select from the 36,000 compensation values. We're going to do in this loop 100 times the following. Take a sample of size 500, bootstrap it, compute the left end, compute the right end, and repeat. Take another sample, bootstrap it, left end, right end. And then at the end, we're going to produce a table that has the word left and right. We'll put the left ends and the right ends. And I'm going to go ahead and run it. Okay, so it'll be 4 minutes until we actually can mess with the worksheet again. But while we're waiting on it, what we'll get from the output is something that looks like this. A bunch of left values and a bunch of right values. And so this is an interval. It's one of those yellow bars. And we'll just wait it out. So we got about 4 more minutes together waiting on this. And the reason it takes 4 minutes is it's just wants to. So we're doing, we're actually doing 500 times 5,000 times 100, fairly extensive operation. 5,000 times 500 times 100 operations that involve 36,000 things. So it's there's a lot of little rats running around the computer right now. So the reason I did the HTML rendering is in case this actually breaks, we can go look at what it's supposed to look like. But I wanted to do it live, mostly to show you that some things we do take a long time and we have to be patient. And then for the good,
you have a few moments, maybe you can give a student some information about the Thursday costume class.
Well, just wear a costume if you want to. Anything that vaguely resembles a costume will count. And I have a former student who I'm hoping will be able to join us to do the actual judging. That way I don't have to judge. And whichever one she picks as the best costume will get the 50 extra credit, and any costume counts for 10. And if you don't want to wear a costume, that's fine. The point value isn't going to make that much of a difference, you know, in your ultimate grade, but it's of enough value that it's worth your trouble if you're into costumes. And so what's okay? Let me say what is not acceptable costume. It has to be something that you could wear at, say, United Market and not get arrested. So that I think should give you plenty of latitude, but you could just be a mummy and raptor. Max, where are you going to get toilet paper this day and age? So that's the only criteria. You have to cover enough of your body parts that you would be able to go into a public place and not get arrested. No costume malfunctions, please, from any participants. Yeah, that's a lot of slack, Brandon. Let's see, the other criterion is can't be offensive. Can't be offensive. So I'll leave it at that. And that should be sufficient. So examples of what things have done in the past. I can give you some lame costume examples. So if you happen to be a dude and you have a big old fluffy beard, you throw on a plaid shirt, and you get a roll of paper towels, and you go as the brawny man. Okay, easy costume, no brains required. So that would count as a costume. What is one in the past? So Ileana asked a fair question. Our computer is still grinding away. 20, see, when did I start? Like 24, 3, so 1 minute to go. Things that won in the past, one person came as Max from Where the Wild Things Are. He was one of the creatures. And that was an impressive costume because the guy had to walk from his dorm to the classroom across campus wearing that thing. Other things that have won, one person came as a 100-year storm, which makes no sense to you all, but it was relevant for the class that it was being taught at the time. Another one came as Iron Man. That was a pretty damn elaborate costume, although I think they bought a lot of it, but they still had to figure out how to put it on. So does that help you, Ileana, give you some context? The 100-year storm was actually brilliant because it was a tutu, tights, and she made the upper part of the ballerina costume had what she used for the puffs of cloud. I don't think it was cotton balls, but it was something really easily obtainable. I think it was just, oh, I know what it was. It was stuffing that you put when you stuff pillows, if you're making throw pillows. And it was pretty creative. And the particular tutu she had, she was able to put lightning bolts and raindrops on it. So the costume wearer was into theater arts anyway, so had all the stuff laying around and just probably threw it together in less than an hour, but it was brilliant. So it doesn't have to be super elaborate. Also very popular are devils, because devils is really easy. But I think anyone, if you do a devil, that's fine. But if you don't paint your face red with red face paint, it doesn't count. That's just a pseudo devil. We're going to do a voting, and then again, if my friend can attend, her vote is the Electoral College. So we can have a popular vote winner and an Electoral College winner. It'd be cool if they're the same, because then they get 100 points, but if not, then each of them gets 50, and everybody who tries gets 10. So, you know, that's the whole everybody gets a trophy. We can't depart from that. Okay, our simulation is done. Is that enough background? Okay, let's get apolitical again. I'm sorry I brought that up. I regret that. We've just done the simulation. So now let's look at our intervals. So here are our intervals from 106,000 to 119 and so on. So there's 100 ones. And the good intervals are the ones that contain the parameter we're trying to estimate. In this section, we happen to know what the estimate is, 110,000. And now we're going to count the number of intervals where the left is below this value and the right is above this value. We want to count how many intervals contain the population median. We run that count, 94. We were shooting for 95, that's not bad. So it took a few minutes to construct the intervals. So about 95 to 100 were good. They contained the parameter. In our case, it was 94. It's hard to show all the intervals on the axis as there's overlaps. So instead, we're going to generate a graphic that's going to stack the intervals vertically. And the vertical axis is simply the number of replication. The horizontal axis will represent the interval estimate, and we're going to produce a red line which represents the population value. So good intervals will cover the population value, and ones that don't cover will leave open spots. So before I run this script generation, so for example, where the cursor is right there, that interval does not contain the population value. This interval does not contain the population value. That one does not contain the population value. There should be more that, let's say 94. So I should be missing 6. There's 1. Oh, this is a different picture, that's why. So let's go ahead and run the picture. This is a pretty cool picture. It's actually kind of cool how it's done. You can actually put the plot into a loop. And so we're going to build a figure called figure. And then we're going to append to the figure the plot of the ends. And then we'll throw on the population median, X label, Y label, title. So here's our results. So that interval, 1 does not contain it, 2, 3, 4, 5, 6. But most of the intervals, 94 of them, contain the population value, the red line. And so we can state that our 95, actually, let me see if I can replace that. So to summarize what we've just shown, suppose we're estimating population median by the following process. Draw a sample from the population, bootstrap it, repeat the bootstrap thousands of times to get thousands of estimates, pick off the middle 95% of all the estimates. That gives you one interval estimates. Now, if you repeat it 100 times, then about 95 of those 100 intervals will contain the population parameter. In other words, the process of estimation calculates the parameter about 95% of the time. You can replace the 95 by a different value, so long as it's not 100. Keep the sample size fixed, and then your interval estimates will be shorter because the middle 80% is smaller. Now, the whole point of this, in general, we're only going to be able to make one interval estimate. This is how statistics are invented, how they come up with the T statistic or the Z score or something. If they run simulations like this, and we'll design a statistic which keeps the red line in our population interval. And then from that, we can just use the statistic and use the interval estimation principle that we alluded to earlier. So if they happen to be normally distributed, what we know from way back up here, somewhere way back up here, if it's normally distributed, then we will, with 99% probability, capture the population value if we make our intervals plus or minus 3 standard deviations, either in the original scale or plus or minus 3 standard deviations in Z-score scale. The deviations will have different value if you go to Z-score scale, but it's the same thing. If it turns out that our underlying distribution is something different, then the statistic might be different, and the plus or minus standard deviations would be different. So that concludes an introduction to interval estimates and bootstrapping. And the reason both those had to be presented is that bootstrapping is referred to quite a bit in interval estimates and in professional literature. But our goal is to come up with one of these yellow lines for our data sets. And if we're doing it from scratch or we don't trust our work, we can do the simulation technique to get somewhat of a more comfortable estimate. Although if we're simulating it on real data, we'll never be able to get the red line. But we can get a look at what the interval estimate looks like. So this particular simulation here of 100, it's kind of wobbling a lot more than I would be comfortable with. So what we're kind of hoping for is it is mostly centered on some interval, maybe a few white spots in there, and not wiggling left and right quite as much. I think that's a consequence of the random pay scale of the city of San Francisco, which is in California, which is the land of nuts and honey. Okay, I will shut this down now and then take a few minutes break, and we will return with Lab 17, which you can access either from this interface by going to Laboratory 17, there we go, or you can go from Blackboard, and click on the Lab 17 direct link. Boy, I hope it works. It does. And when you are completed with Lab 17, you can upload it here in the usual place. So with that, I will stop sharing. I will hand over control to my colleague. Somehow. There he is. You are the boss.
Thank you. Thank you very much. So if you all want to go have a break, you have 5 minutes. I'll be here if you have any questions. Let me actually go and share my screen. You will need to you need to download Lab 17 underline class notebook file. That's all you need for this week. Let me open my chat box. Carson, that is a good question. I'm not sure, but I think it will be enough to wear it at the beginning of the class. Mishael, these are good questions for Dr. Cleveland because he's the one regulating this whole thing. I would say you will need more than that, but I really don't know. I do have so many tabs open, and in fact, I have so many windows with so many tabs. So that's one of my, I guess, bad habits. That was the Lost Mines of Vandal, yes. Why? Because like I have one window and all its tabs related to one of my papers, another window to another one of my paper, another one with the stuff that I need to prepare your lab notebooks, another one for my gaming and stuff. So yeah, you could say that, but there are some of us that are kind of more, I want to say, clean. Yeah, for example, my wife is also a PhD student, but she only has one window and like 2 or 3 tabs at each time, and then she closes everything. I basically do not close tabs until I'm 100% sure that I'm not gonna need them anymore. So yeah. Yeah, I am married. Yes. Yeah, maybe one day. She's also a PhD student at Tech. My RAM is on fire. The good thing about Chrome is that if you restart your computer, you can get all your tabs in, but as long as you do not click on them, they will not load. So they will not be as engaging with your RAM as some terrible explorers like this one. So, are we all ready? I should have participants, 57 participants, which is good for a snowy day like this.
That's a cool gift.
The recording should be on because I think Dr. Cleveland didn't stop it. So let us go ahead and begin our lab session, our lab 17. And today we are going to talk about confidence intervals and A/B testing. The meme that you're seeing here is for those of you who really love statistics as we are going through different topics. And since we both, Dr. Cleveland and I, know how much you are enjoying these last few weeks, we thought this would be a good representation of your feelings for this lab. So for the information box, you know what to do at this point. I trust you. You're going to fill in with your own information. In our first example, we are going to talk about football and Italy. And football is the same sports that you guys call soccer in the States. And I have put this map here for you to basically tell you that football is the right name of this sport. I know that it is hard for you to break this habit, but the name is football. And if the name was soccer, they would have called it SIFA, not FIFA. So actually, this is Iran, and they call it football in Iran as well, because that's not a Persian word. We just use the original version. That's one of the better things about Farsi or Persian. So now that we have put that beside us, the question that we are trying to discuss here is how many people love soccer? So if I put up a language map, then the one with the most spoken is the right language? Not necessarily. The reason that I insist that football is the right term is that because it was invented by the British and they called it football. And that's it. That's the name. And yes, Abdul, I noticed that many of my American friends here have played soccer sometime in their lives. So it is a popular sports here in the States as well. Maybe not as much as in other countries, but there are many people here that like it. So I'm not gonna spend more time on this soccer football thing. This could have been a whole discussion, but we are kind of late on the lab, so call it whatever you want. For your sake, I've called it soccer in this lab as well. So we are going to work on this example in two modes: the God mode and the man mode. For those of you who are into gaming or other kinds of programming, God mode may have a specific meaning. By God mode in this example, we mean that we are assuming that we know everything about our population. In this case, the population of Italy. And we are assuming that we know the exact percentage of people in Italy that love soccer, and it's 75%. So if I look at the population of Italy, 75% of them love soccer. That is a piece of information that we as the God know in this specific mode. And we are going to assume that we want to know the chance of randomly selecting a group of people, let's say a group of 1,000 people. And we want to know what is the chance that this group, this sample that we're taking, has only 73 people, 73% of people that love soccer. So this group of 1,000 people, are they going to be my population or my sample? Sample, yes. It's good that we know that. Cool. And when we are talking about this 73% here, what is this? I'm looking at the chat box. Share your ideas. What is the 73% that I'm looking for? No, it's not percentile. We want to know the chance of randomly selecting a group of 1,000 people that only 73% of them love soccer. Mean of population, you're getting kind of close. Didn't we just, okay, yes, mean of sample. Very good. This 73% is our mean of sample. What is our mean of population? 75%. So Rami, so only like 730 of 1,000, the chance. Yes, it basically means that if you ask 1,000 people about their opinion about football, soccer, 730 of them is going to say we love it. The rest will say we don't like it. So in the God mode, we are assuming that we know the population mean, and we are interested to know what is the chance or what is the probability of selecting a sample with the size of 1,000 and get a sample mean of 73%. Do you get the question? One way or another, confirm that you are okay and comfortable with the question that we are asking here. So we know the population mean, and that is 75%. We are interested in knowing the chance of selecting a group of 1,000 people randomly and get a sample mean of 73%. So 2% below the population mean, if you may. So for 54 students in the class, only 2 confirmations is kind of low. So if you do not understand the question, ask. If you do, makes sense. Okay, Brayden, the pop is 60 million, which makes more sense. So infer something about a smaller sample than what we know. Basically, Dule, what we are trying to ask in this case is that we are assuming that we know our population, and we are asking a question about our sample. So I think what you were trying to say is correct, if that's what I said. Okay, so let us move on. To answer this question, we will take multiple steps. Wherever you had a question, ask and do not let it just pass. So I'm creating an object for my total population. And since we know that we have 60 million people, almost 60 million people in Italy right now, that will be 60 million. The percentage of those who love soccer will be 75%. And then we are calculating the population of Italy that loves football by basically multiplying these 2 numbers. And then the rest will be the population who doesn't love football. Is that clear? Okay. So on the next step, we are going to create a NumPy array with 60 million elements, with a 1 for each person who loves soccer and a 0 otherwise. So before going here, I want you to read these comments. Do not attempt to print the objects that we are about to create. That will probably break your computer or be very hard to manage. I really don't know what will happen on your machines, but I just suggest that do not print it because it's going to be an object with 60 million elements. So I doubt it that it's gonna cause your CPU to explode, but let's just not try that. So I'm importing NumPy because I want to create a NumPy array. I'm creating a NumPy array of 1s. How many 1s? The number of population who love soccer. And then another NumPy array of 0s. How many? The count of population who doesn't love football. And then I'm putting all of those together. So in my .pop underline 01, I will have a giant array with 60 million objects. I will have 11111 for the part of the population who loves soccer, which will be 75%, because we know that, we already got. And then some 0s for the part that doesn't love football. That will be 25%, of course. So just to check that we have done the right thing, we are going to get a mean of this object, and we expect that to be 75%. You should know why this should be 75% at this point. If you don't, ask. Are we good? Okay, cool. Now, let's take a few samples from this giant array of population that we have created. Basically, this TOT POP_01 is our population. And the only reason that we know our population is that we are in God mode. So let's go in and take a few samples out of our population and calculate the mean for those samples. So what is our sample size? 1,000, because the question has asked for it. And then I'm basically randomly choosing 1,000 objects and calculating the mean. If I run this once, it will give me a mean of 75.6%. Then if I run it again, 75.4. If I run it again, 73. That's actually what we wanted, right? And then 75.7. So if you run this multiple times, you will get different numbers. Does that make sense to you? Did you expect that we will get different numbers, or did you expect that we will always get 0.75? Different. I expected different. Okay. We are good on the fundamentals then. Exactly, because we are randomly selecting only 1,000 members out of a population of 60 million people. So we expected to get different numbers. But since whenever we need to do something repetitively, we don't like to do it like what I did here, like keep running something. We want to do it in a more sophisticated engineering, data science-y, and for the case of at least one of you, scientist-y way. We are going to create a simple for loop. And let's say that we want to take 10 samples, and we will basically repeat our sampling and calculate the mean. So here you see that out of my 10 samples, I'm getting these values for mean. So sometimes it goes up to 76.6. Sometimes it goes as low as 73.8. We are getting values close to 75, but not exactly that, which is what we were expecting. Braden, I'm not sure what is happening on your side, but if you are not using CoCalc and you're using your... Okay, that is expected. If you are using CoCalc, running something with 60 million objects is going to cause that to die, basically. So you can either just follow me. The best way would be to run this on your Jupyter, on your local machines. But if you're going to use CoCalc, you can either just follow me or go up here and assume that you are working with a country that has like a population of 5 million people. So you change this to 5 and you should be good. But that is another limitation of CoCalc. So let us move on. You can see that we are getting different values for each sample, but the intuition says that the average of large amount of samples should be very close to the real percentage. By real percentage, we mean the population mean. So what is the meaning of that sentence? Do I have a volunteer who wants to tell me what is the meaning of that sentence? This one. The average of large amount of samples should be very close to real percentage. So if you want, you can unmute yourself or you can type your opinion in the chat box.
So is that basically saying that like the sample of a large population is just going to be close, like it's just going to represent whatever our population is? And the mean of the sample will be close to the mean of the population?
You are not being 100% accurate, and you're missing one tiny point. So a sample of a large population is not what we're talking about. We are talking about large amount of samples. So basically what this statement means is that if you are able to take many samples, you will have a high chance to estimate the population parameter, in this case the mean, very closely. Exactly, Rame. So by taking many samples, you are trying to capture different parts of your population, and by putting all those pieces together, getting a better representation of that entire population. So in this case, we have said, okay, let's take more samples. Instead of 10 samples, we are going with 10,000. And if we do that, if we take 10,000 samples, for each sample, we calculate the mean, and then we calculate the mean of those means, we are going to get this number. So don't let this confuse you. I have a population of Italy. I'm taking 10,000 samples. How many people do I have in each sample?
1,000.
1,000.
1,000. So I have 10,000 groups. In each group, I have 1,000 people. I'm asking their opinion about football. And from each group, I'll get a mean, correct? How many means will I have?
1,000? Wait,
10,000. Because
yeah,
for
10,000.
each group, I will have one mean.
Right.
Then if I calculate the mean of these 10,000 values, I will get this. So is this value close enough to the population mean? Yes, yes, yes. So that is exactly the theory that we were talking about. So if you take large amount of samples, many samples, in this case 10,000, you will eventually be able to closely estimate your population parameter of interest. So I actually went ahead and calculated the standard deviation of my population as well, which turned out to be about this. When do we use that? You will see later. So we created 10,000 samples. We checked the percentage of people who love soccer in each sample, and then just averaged them. And we managed to get very close to that 75% value that we already knew because we were in God mode. Otherwise, you wouldn't know that 75% of people in Italy love soccer, right? As mortal human beings, we do not know our population. So we want to go on and plot a histogram. Let me see, I think I have to run the cell. And then I can go ahead. Okay. Looking at this histogram, you should be able to tell me some information about my population. So either use the chat box or unmute yourselves and tell me, what does this tell you?
It looks normal.
It looks like a normal distribution. Very good.
It's probably Gaussian, and then for some reason there's like a huge data value around, I'd say 0.755.
Okay.
Like there's a spike, but medium is around 0.75.
Okay, so the center of this is somewhere around 0.75. What else can you tell me about this? Yes, what else can you tell me about this? Mishael, you said standard. It's not a standard. So it is something that you already had faced in your midterm 2 as well. We have normal distribution and we have a standard normal distribution. The standard normal distribution is a special case where your mean, median, and mode are all equal to 0. So if this center was right at 0, it would have been a standard plot. But in this case, it is not a standard. So Dr. Cleveland says 3 standard deviation is equal to 0.05. And do I have anyone who can tell me how he got that number? What did Liliana say? Values are very close together because of a small standard deviation. It's some future warning, apparently, and I'm confused about the error message. Endpoints. James, yes. So if you notice, we already said that our center is located at 0.75, but if you move like 0.05 points to the right, you will be at 0.8, which is kind of the endpoint on the right side, and then 0.7, which is kind of the endpoint on the left side. And data spread from the mean or from the central location, that is equal to 3 times standard deviation on each side. So that's how Dr. Cleveland said that looking at this histogram, we can say that our standard deviation multiplied by 3 will be equal to 0.05. Okay. Let's assume, do not run this, and I will tell you why. Let's assume that we want to increase the number of our samples. So instead of 10,000, we want to go for 1,000,000 samples. If you notice, I've turned these two into raw cell types rather than code because I didn't want you to run them by accident. Running this will create 1,000,000 samples with the sample size of 1,000 out of your population, and then plot the histogram. This will run, but this will take a while. I would say maybe around 2 or 3 minutes. And if you have time later, do it. If you're on CoCalc, I recommend not doing that because it will probably crash and stop your server. Okay, cool. Thank you, Dr. Cleveland. So our custom judge will join us at 8:30 on Thursday, and that's when the contest starts. And Ileana says that we can probably do a poll on Zoom. I'm sure there are online things that we can use, but that was the additional piece of information that you need for our special session on Thursday. So looking at this histogram and even the one with 1,000,000 samples, there are a few things that we can say. We've already discussed them. We can see that the center, the mean of the histogram is near 75%, exactly as we expected. We are able to say much more. We can, for example, say that the sample, almost half of the samples are larger than 75%, and roughly 25% are larger than 76%. We can also say that almost 95% of the samples are between 72% and 78%. What are we talking about? Look at 72% and 78%. This area in between 0.72 and 0.78 contains 95% of our samples. Does that make sense?
Yes.
Yes, and thank you, Braden. 2 standard deviations. Very good. Yes, Jaron, that will take a while to run, as I said. But don't give up on it. It will run. So after the histogram, we can actually have a look at the box plots as well. So kind of similar observation. We are seeing that our median is located at 0.75. The majority of our observations are between 74 and 76. 75% of our data falls below 76%, and 25% falls above 76%. So we can kind of observe similar things with our box plot as well. So at this point, many people might ask two important questions. How can I take infinite number of samples? And how does it help me? For the first one, you can only take infinite number of samples if you are God, or if you are in God mode. If you are not, you can't. That's part of the deal. That's life. And then to answer the second question, let's recall the question that we were trying to answer. We initially took one sample of 1,000 people and got a value close to 75%, but not exactly 75%. That this goes back to the first time that I took a sample of 1,000 people. We wanted to know, what is the chance that a random sample of 1,000 people from Italy will have 73% soccer lovers? Using the information above, we can say that there is a chance of roughly 20% that we will get a value that is smaller or equal to 73%. So even looking at the box plot, you can kind of get that. If you look at the histogram, 73% would fall here. So this part of the plot will be almost 20%. The good thing is that you do not actually need to take infinite samples. Or in other words, you do not have to be God to be able to answer a question like that. You will know why and how in a few moments. So on the next step, we are going to look at this from the man mode. We are getting out of our God mode and we are stepping back into our horrid and miserable man mode, where we do not know the actual percentage of people who love soccer in Italy. In fact, we know nothing about the population, just very similar to the examples that we discussed in the previous labs. Do you remember the example that I told you about me going to a river and take samples and measurements of a stream flow? The only reason that we do that is because we do not know our population. If we know our population, there is no point in making samples. So what do we know? We do know that we took a sample and we got 73%. So let's say I was interested in knowing how many people, or what is the percentage of people who love soccer in Italy. I went in and I randomly asked 1,000 people in Italy from different parts of different ages, completely random. And I calculated that value to be 73%. How does it help us? What we also do know is that if, and that's a big if, especially since we're in the man mode, if we took infinite number of samples, the distribution of their means will look something like this. So this is a normal distribution. At the center of it, what do we have? This mu is basically the population mean, or the real percentage of people who love soccer in our example. And then symmetrically, by stepping, by moving away from our mean by steps of standard deviation, the more I go further to the right, to the left, I'm going to have less and less samples. This is exactly the formation of a normal distribution. And based on this, we are able to say that 68% of the samples will fall in the red area, and more than 95% of the samples will fall outside the green area. So these two plots are very similar. We are saying that by moving from my mean to the right and to the left with the distance of 1 standard deviation, I will be able to capture 68% of my samples. If I go one step more to the right and one step more to the left, I will be able to cover 95% of my samples. Hold it here and let me know if you have any questions or confusions about these two plots. These are extremely important. Questions?
So
Questions?
will it always be like a negative from mu to negative lambda? Will it always be 34%?
Yes,
Okay.
because we are assuming that this is a normal distribution.
Okay.
So a very important and fundamental assumption behind all this is that we are assuming that our population is normally distributed.
Okay.
If you are dealing with a normal distribution, moving away from the central position to the right and to the left with the steps equal to 1 standard deviation, you will be able to catch 68%. Exactly, Max. Rame, so the percentage of the samples on the extreme brine are rare and unlikely to occur. Exactly. So if you remember from our previous discussion on hypothesis testing, we actually said that the less frequent or less probable events always fall under the tails on both ends. So in a normal distribution, we have our central location, our mean, our median, located right in the middle. If we move away from that position with a step equal to 1 standard deviation to the right and to the left, we will be able to capture 68% of our samples within this red area. If we go for one more step to the right and one more step to the left, we will be in the red and blue area, and that will be 95%. And then we can keep going, but we will be able to capture more samples, but the steps, the amount of samples that we will add is not going to be as high. So, do we have any other questions about these two plots, normal distributions and the number of samples that we can capture? Okay, so this is where the concept of margin of error becomes of great importance. So this is a new term, at least in this class, we have not talked about this before. The margin of error is calculated as the z-score associated with a confidence interval, you will know that in a moment, multiplied by the sigma or the standard deviation, divided by the square root of your sample size. So let's see what that actually means. Margin of error, or MOE. Let's assume that we have a normal distribution like this. Do you remember what alpha was? Significance level. Yes. So if I set my alpha equal to 0.05, which is kind of a common practice, and assuming that we are dealing with a two-tailed test, so we are looking at both ends of the distribution, we are putting this vertical line of critical value here at alpha divided by 2, and a similar one here Again, alpha divided by 2. And whatever falls in between of those two vertical lines will be acceptable to us, will be what we will capture within our margins of error. Naturally, if we increase the size of alpha, we will have a smaller MOE, as you can see by comparing the plot on the right and the plot on the left. Smaller alpha, larger MOE. Bigger alpha, smaller MOE. Now, for the last part of this, no, Rami, if you go with an alpha of 0.05, that means that you have 95% left. Because half of that will be on the right and half of that will be on the left. If you notice, this is alpha divided by 2. Did you get it? Yes, no, maybe? Yes, exactly. 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 You good? Cool. So now that we have covered the God mode and the man mode, we are going to kind of mix them and do the mad mode. So we know that because we are dealing with a normal distribution, this is going to be symmetric. And this is an extremely important statement. And I want you to read that multiple times and listen to me as well. If the sample percentage will fall 95% of the time between real percentage or population percentage -3 and real percentage +3, then the real percentage will be 95% of the times between sample percentage -3 and sample percentage +3. So this might sound a little confusing for the first 2 or 3 times that you read it, but notice that we are basically replacing our perspective on the problem. In the first one, we are still in the God mode. We know the real percentage and we are curious and interested in sample percentage. In the second part, we are in the man mode. We know the sample percentage and we are interested about the real percentage. So let's read that again. If the sample percentage will fall 95% of the time between real percentage -3 and real percentage +3, then the real percentage will be 95% of the times between sample percentage -3 and sample percentage +3. Now, I have a question. What is this -3? This number is specific to our example. Rami, you're getting very close. That is equal to 2 standard deviations.
The -3 like your margin of error in this case?
Yes, exactly.
I
Exactly.
wish she was an engineer.
If only. So I was kind of hoping for more questions in the chat box, because when you ask questions, I'm kind of feeling that you're following, and it is very important for me that you understand this part. Rami, isn't that a statement under the same logic as large samples should be resilient? It is, yes. Basically, all we are talking about today is under the same logic. We are trying to move from samples to population in the man mode and move from population to sample in the God mode. But in reality, the God mode doesn't exist because unfortunately, none of us are gods. We only use that as an example. The -3 the minus or plus 3 in this case is 2 multiplied by my standard deviation, is the margin of error, is the step that I will take to the right and to the left from my mean. Brayden, was that a good enough answer? Can I give you an example? Yes, of course. Actually, we have more examples coming up, but in this one that we just covered, we said that we took a sample and we got 73%. So I can actually go ahead and say, let me see, I should have it down here. Yes, I have it here. So let's read this together. We took a sample and we got 73%. We already knew that. That's part of our limited knowledge as mankind. We can say that we are 95% confident that the real percentage is between 70, which is 73 minus 3, and 76, which is 73 plus 3. Only look at this sentence and tell me if that makes sense to you.
Yeah, it makes sense.
I went to Italy. I asked 1,000 random people about their idea about football, and I realized that 73% of my sample likes or loves soccer. So, based on that sample, and assuming that I have an understanding of the standard deviation of the population, I can say that I am 95% confident that the entire population of Italy has a mean of 70 to 76. So somewhere between these two numbers, I will find the real population, the real mean of the population. The 3 is percent in this case, but it really depends on what you're studying. The margin of error is similar to p-value. I wouldn't say that. They can be both defined under normal distribution, but p-value is calculated based on test statistics for statistical tests. Margin of error is kind of different. Do I have any other questions? So when I make a statement like that, that is basically my confidence interval. The interval is 73 plus minus 3, or basically 70 to 76. That's the interval. And my confidence is 95% in this case. Max, the 2 standard deviation in this case is equal to 3. I think you can see my hands better like this.
And is that because the middle value of our graph is 73? So, and if we took the standard deviation of that, that'd give us the right side?
The middle value is 75%.
Okay.
Yes. And then moving 3% to the right and 3% to the left will give us that 95%.
Okay, and then the other 5% is just the outer tail. The other, like the 0.25, as Rame said earlier.
Yes.
Okay.
The further you move towards the tails, you will be able to capture your more extreme samples, but then it really depends on this confidence that you're looking for. So if you want 95% of your samples, you stay within the limits of 2 standard deviations to the left and to the right.
Okay.
If you want more, you will go more. If you want less, you will go less.
Okay, and that makes a lot more sense. Thank you.
Cool. Because of the significance level we chose, I'm not following Eliana. Basically, you calculate your margin of error based on the confidence level that you want. So if you want 95%, your MOE will be calculated based on 95%. If you want 90%, that will be a different MOE and you will capture a different interval. Are we good? Cool. Dariel, the number 3 is basically my 2 multiplied by standard deviation. So yes, my standard deviation is almost 1.5. So 2 times that will be 3. Any other questions? So if confidence was 68, would we use, we would use 1? Yes, yes, you're correct. You're correct. So let us move to another example, and then I will again ask for your questions. So from a normally distributed population, we randomly took a sample of 500 students with a mean score of 461 on the math section of SAT. Suppose the standard deviation of the population is 100. What is the estimated true population mean for the 95% confidence interval? So the first question, are we in God mode or are we in man mode? Man mode. Man mode. Ilyana and Max, since we know our information about the sample and we are interested in knowing about our population, we are in man mode. Clear? Cool. So let's organize the data. Let's see what we have. We know our sample size. We have 500 students in our sample. We know our sample mean, which is 461. We have been told the confidence level that we're interested in, which is 95%. The standard deviation or sigma is given to us as 100. And we know the z-value associated with 95% confidence interval. How do we know that? There are actually tables for that, but since you are living in the beautiful era of internet, you can just go and Google for Z95 confidence interval. And it will give you a table like this. Since you are interested in confidence interval of 95%, you will just simply cut this number and bring it back to your notebook and put it here. Ta-da! So one more time, it's Google to rescue. And Max, that is correct. If we were God, we already knew everything about the population and we could answer the question easily. Yes, Z-score tables are cool. And that was the most scientisty thing that one could say. But you can use those, or you can use Google like I did. Either way, it's going to give you the same number. So there are 2 important assumptions that we need. Exactly. As Dr. Clement say, you can use our function or the function that we have used multiple times, you've used in your exam, and find z so that the norm dist of z and 1 is equal to 0.95. That's another way. We are building our calculations based on 2 important assumptions. The first one is that our population is normally distributed. Actually, it is given to you at the beginning of the question from a normally distributed population. Make sure that you notice that. And then we are also assuming that we are randomly selecting our samples. What do we mean by that? It basically means that we don't want any relationships between different samples that we take. Let me take you back to my Italy example. If I went to Milano, Italy, and I actually went to the neighborhood around the San Siro Stadium, for those of you who are into Italian football. If I took my 1,000 samples from people who lived there, that wouldn't be fair, because there might be people living near borders or in mountainous areas or areas very far from football fields, and they wouldn't be as much interested in football as someone who goes and purchases a house or an apartment just next to a football stadium. So we want to make sure that our samples are completely random. That's another important assumption. On step 2, we are going to calculate our MOE, or margin of error. How? Using this formula. We already have our Z from Google or from table. We have our sigma. The question is given that. And then our sample size. So here, I calculate my margin of error. I'm actually importing math because I'm going to use the sec003 function. And then if I run that, I will get my margin of error to be equal to 8.76. So now that I have my margin of error, we are going to find the estimated true population mean for the 95% confidence interval. To find that, you simply add and subtract the margin of error from your central value, in this case 461, which is your sample mean. So your low will be X bar minus margin, your high will be X bar plus margin, and you can print something like this and say the true population mean will be captured within the confidence interval of 452.23 and 469.76, and the confidence is 95%. So if instead of 95% confidence, I was looking at 99%, what do you think would happen? What would be different? Would my N be different? No. Would my X bar be different?
No.
Braden, if instead of 95% confidence, I was looking at 99%, would my C be different?
Yes.
Yes. Instead of 95, it will be 99. Would my standard deviation be different? No, 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 no. Would my Z be different?
Yes.
Yeah.
Yes. And that is the important part. So by changing that percentage, that confidence level, you are changing the Z, and that Z will change your margin, and that margin will change your interval. Did you understand this example? Do you have any questions about any part of this example? Okay. So you have one exercise to work on. From a normally distributed population, we randomly took a sample of 200 dogs. And this is dogs because I came up with this example. If it was Dr. Cleveland, it would probably be 200 cats with a mean weight of 70 pounds. Suppose the standard deviation of the population is 20. What is the estimated true population mean for the 95% confidence interval? How about 90% confidence interval? How about 99% confidence interval? And I believe you should have no difficulties tackling this exercise given the examples that we covered. Dooley, that is completely correct. As a human being, you will never be able to be completely certain and accurate about a population. So you come up with the statements. And that could be looked at from a liability issue. Exactly. So I have listed some great reads and some great videos for you on confidence intervals. I of course recommend you to have a look at all of them, but if you are limited on time, at least to spend some time and watch the videos. They are pretty good, especially this guy Josh Stormer. I really like his videos on different statistical topics. He has a channel on YouTube called StatQuest. I don't know if you have worked with his videos before or not, but I definitely recommend them. So if we want the true population mean, we should become God. Yes, exactly. So Dr. Cleveland, I have a question. We are at 10:40. Shall I begin the A/B testing part, or shall we leave that for next week, for next session on Thursday?
Next week.
Apparently they want to wait till Thursday. So, okay, so we'll do it on Thursday, but you all have to do some homework. You need to read the data inference textbook that we're supposed to use in the class. Find the section on A/B testing, and not only read it, attempt to work through it, keeping in mind that the scripts that they provide will not work because you don't have all the dependencies built in. But most of them are based on NumPy and pandas. And at the end of that, on Thursday, we'll start off with A/B testing, at least on the Thursday lab. I'm going to continue on interval estimates in the Thursday lesson. And yeah, someone's saying, do you guys know how to read? Rame, if you're illiterate, that's a shame, because that kind of, if you break it out, it means ill, which is sick, and then iterate. So you need to iterate your sickness repeatedly. So that's fine with me. If you all agree to read, and then on Thursday at 8:30, Marion Schwartz is going to join us for a little while to judge your costumes, and I've explained to her the game already, and she understands her role as Electoral College, and that won't take that long. Hopefully less than 20 minutes, but I mean, we're going to make sure that everyone gets a shot at it. And I'll just remind you that today you've got to experience politics, engineering, statistics, and theology, all in the same lesson lab things.
Hell
can't
yeah.
get-
That's why we are definitely the coolest class that you have this
Yeah,
semester.
you can't get that anywhere else. Only at Texas Tech, and only with Farhang and Dr. Cleveland.
So guys, for this lab notebook, you only need to worry about exercise 1 at this point. We will cover A/B testing Thursday, and we will probably have another notebook for lab 18, which goes hand to hand with this one.
So with that,
I'm gonna stop sharing. I'm gonna.
yeah, I'm going to shut everything down. I have another class in how many minutes? I think 20. Oh, 15. Yeah, that's plenty of time to prepare a class.
And my era as the god has become to an end.
Okay, so
Dr.
for
Cleveland, you're God again.
today's video, I started recording the video kind of at the last part of the lesson. I'm just going to render the whole thing as lab, whatever number on, lab 17. So because I didn't start the video in time to be useful on my part. So have a great day. Have a good afternoon, everybody.
If you need a Zoom link for a meeting with me, just email me right now and I will send you the link.
Okay, let's see. Anything else? Any other announcements to make? I think that's it. Be very careful. Stay indoors today if you can. So that you don't become you don't become a statistic. Because we don't have a gift for that.
Or you will be the gift.
Yeah.
See you on Thursday, guys.
All righty. Bye-bye.
Bye.
Oh, the truck has been towed away and the tree looks pretty okay. So with that, have a great day, everybody. Bye-bye.